We can start the last session of the day. And to start with, we have Andy Gordon, who is going to talk about multi-agent system for traceable Bayesian workflow.
Great, thanks, Guillaume. Great to see everyone. This is joint work with Hong Gay at University of Cambridge and our student Xianda Sun. Xianda's student couldn't be here today, but he's on WhatsApp and he's watching the live stream. So he's my backup if I can't answer your questions. Great, so what is this about? What's the motivation? And basically, we want to solve Bayesian modeling and automate the Bayesian workflow. So we today, if like a scientist scientist, a social scientist, computer scientist, whatever, you've got a bit of data, you want to do a Bayesian analysis of it. Today, this is pretty hard. There's a lot of iteration. If you're not an expert, there's a lot of pitfalls. We wanted to see if we could automate that. To some extent, probabilistic programming languages have always been trying to do this, but there's a number of things like checking good fit of the model and a whole bunch of things, choice of model, that are sort of outside the scope of the core probabilistic programming language itself. So we're trying to use prompts to large language models as a sort of language for inference to describe the whole process of doing Bayesian modeling. So we're going to be formalizing this kind of loop. So what we're going to do is build a multi-agent system that orchestrates existing tools. We behind the scenes, but I'm not going to show you any of its code, we use Stan as a probabilistic modeling language. But we use a whole lot of other tools as well to visualize the data and to look at sort of analyze the fits of the model against the data and so forth. All these kind of steps we want to orchestrate, and we get two outputs. One is we get a model that passes validation checks on the data we've given it and work well predictively. And also we get exploration traces. So we get a long trace of all the work that the machine has been doing while following our prompts as it tries to follow through on the Bayesian workflow. And this trace documents models that were considered failures and revisions. And that's what we do. And we think we're the first to do this, and we think it's an important thing to do, as you'll hear. So firstly, what do we mean by an agent? I'm finding it possible some people know about agents, some people do not. For those who don't, so AI's been around for a while. GitHub Copilot came out 3-4 years ago, and it was like AI autocomplete. As you know, you type some stuff and it would autocomplete the rest of your sentence when you were writing code. Since then, and particularly last year, a lot of the energy is around what are called AI agents. And they have some kind of agency, meaning they've got an ability to perceive their environment, reason about a goal that you've given it, and then to perform multiple step actions using tools. And this is, there's a group in London that hosts something called the AI Native Dev Landscape, and a great website that is a kind of roadmap, a landscape of lots of different AI tools that are being developed in academia and in industry. And this is a screenshot of like different AI agents. I think there's 124 on their roadmap, but I'm highlighting some of the famous ones. So the one that maybe is most famous just at the moment is Claude Code from Anthropic. There's also Codex CLI from OpenAI, and there's Gemini and Google Anti-Gravity, from Google, and a whole lot of other ones. So these tools, you basically give them a command and then they'll execute a while. And they can issue shell commands, they can issue a bunch of things to get some work done. I am completely losing track of time. How long do I have to go? We still have 5 minutes. 5 minutes, okay. So this is a diagram of what we build. So it's like a loop. This is what you go through when you do Bayesian workflow. You start off by doing exploratory data analysis, and in our prompt we tell the AI agent to test at least 2 to 3 competing hypotheses. This is what we put into the prompt, right? We don't write code to do this, we put it as a prompt. And then there's a design phase, and we'll say, for example, explicitly state what evidence would make you abandon each model. So we're getting it to be critical as well as designing models, and it builds a little ladder of models it wants to try. And then it goes into a loop where it tries to apply these models. And given a model, it does a number of checks. It does a prior check. It checks that the data generated from the prior has plausible scale and support. It also tries to simulate data from the model with known parameters and then sees if model fitting can actually recover those parameters. And if these fail, sometimes it will try and adjust, it kind of loops and it will try and adjust them. Other times it just throws away that model saying it doesn't work well. We'll have to try another thing. And then it does fitting, and it runs various convergence diagnostics, builds trace plots and so forth. And this is, remember I said the key thing of our method is we generate a trace of what we've developed. And these kinds of diagnostics, the plots and so forth, get dropped into this trace. So we're building up evidence of what we've done. And this is evidence that is looked at by the model. The model is aware of it. So as it goes around the loop, it can look at previous work that's happened. So it makes better decisions that way. And then it finally has an evaluation where we run posterior predictive checks to see how well the model can generate predictions of known observed data. So that's the main loop, and as I say, it generates an expiration trace. And finally, green at the end, we produce a synthesis report that is the end of it. It's the report back to the person on how the data analysis has gone. Why is it multi-agent? Basically, because it doesn't work if you just ask it to do Bayesian workflow in one prompt. You've got to break it down into multiple prompts, and I don't have time to really elaborate that. It works much better if you break it down into prompts. This is the program, right? This is all the code that we've written, as it were, that defines the Bayesian workflow, and it's a bunch of markdown files. Okay, it's not. That's why I'm saying it's 1,228 lines of prompt. So this is programming in natural language, right, as a collection of markdown files, and some of them are agents and some of them are skills, which is particular jargon that Claude has for basically subroutines that the model can call to get work down. And yeah, that's the gist of that. I've got an example. So this is the system prompt. It starts off saying you are an autonomous technical agent specializing in Bayesian modeling, statistical computing, and software engineering, and this goes on for hundreds of lines. I wanted to give you a gist of what it was, so I put it into Claude and say, summarize this, for a presentation, until Claude came back with this, which is its summary of that, and you can see what we're saying in the system prompt. Like we provide various core principles, tell it about how to use a to-do list, tell it it can run parallel sub-agents, and so forth. And then basically, or crucially, in red here, we've got 4 phases. I'm not quite sure what happened to 4 and 5. Maybe we can ask Xianda. But those are the 4 phases that it performs. That's the loop I was talking about. Very quickly, an example. This is a famous data set of cars with their mileages and their weights and the number of cylinders from the 70s and 80s. And this is an output from the first phase. This is the EDA. We're just getting it to look at the data, literally look at it in the sense of making plots. And in this phase, it's making some hypotheses about what model would well fit it. And basically, it's going to come up with a model that fits this trend here of how the miles per gallon varies versus year. And then again, a key part of our method is that we generate this huge exploration trace. I don't have time or space to show you it, so I asked Claude, give me a summary of what happened in the exploration space, which is what you see on the right there. And basically the gist is, while it did the ADA and it figured out that weight was very important, and it notes some statistical jargon, the severe multi-collinearity, the origin, like where the cars come from, seems to have a large effect. And then during model design, it came up with 9 experiments it wanted to do based on different model classes. There was a simple physical one, and then there were other ones that combined the origin in as well in different ways. And then it ran the modeling. And what happened was that the first class of models was validated, and the other 2 ones were skipped because it found that this apparent origin effect, like, as I say, whether it was from Japan, Europe, or the USA, turned out not to be needed once you look carefully at a simpler model. And then it produced a report. And here's the final model. Sorry, it's a bit small, but it's a simple sort of linear regression where basically the log MPG is being predicted by the weight plus the year. So it does a nice job. We wanted to do a comparison with the closest related work, which is a system called BoxLM. And this chart basically is showing that we get very similar performance. The blue points are actually human-written reference models. This is a bunch of data sets from PosteriorDB, and this is a measure of goodness of fit, and higher is better. And you can see that basically the orange models that have come from our system are actually nearby and sometimes a little bit better than the human-written models. We don't, and sometimes it does worse, to be honest. BoxLM also did worse here. It's a little bit hard to completely compare or fairly compare with BoxLM because it's not open source, and they actually used an older model than the one we were using. So I do some details about that, but if you really want the details, please ask me. Here's a summary of a comparison of this compared to earlier work. There was a ton of work on, like, starting with the very famous automatic statistician from about 10 years ago that was trying to automatically generate just models. And they had quite a limited search space, and our more recent work, such as us or BoxLM, are more open-ended, like arbitrary stand models. But the focus of the earlier work was at discovery, and it didn't look at traceability. It didn't build up this story of trying out different models and then kind of explaining why you made a decision about the final output. And that's really what's unique to our system. BoxLM did not do that to the same extent. So I will end there. I can't resist putting this up. This is a meme from 3 years ago when just after ChatGPT had come out, and people realized that, or Andrei Karpathy realized that, the hottest new programming language was with English. Well, at LAFI, I'd like to just proclaim that I think the hottest new language for inference is English. So thanks for your attention.
Okay. Any questions? A lot of questions.
Hi, very exciting.
Thank you.
Quick question. Did you folks notice any situations where the LLM fails in the way how it reasons about statistics?
Where it fails to reason about?
Yeah, if there are some spectacular failures of runs.
Yes. I mean, yes. Sorry, I didn't emphasize that. I went quite quickly. In that chart I showed, I think there were 18 orange points, and there were 6 that weren't there where the inference had failed. Like where, say, like I mentioned, various reasons we might reject a model. So those 6 models got rejected. So that definitely happens.
One other quick question.
Do you adjust at all for multiple hypothesis testing? Because, like, if an LLM is testing, like, hundreds or thousands of hypotheses, then, like, the threshold for accepting should probably be different.
What do you mean? What kind of hypothesis testing?
When you do multiple regressions, that in just classical statistics, then you have to.
You mean in non-Bayesian statistics?
Yeah, non-Bayesian statistics. Like you lower your p-values because it's more like when you're testing for tons and tons of things, it's more likely that one of them will just seem true by chance.
Okay, we're not doing sort of classical statistics here. We're very much doing Bayesian statistics.
Sure, but the same phenomenon still happens in Bayesian statistics. I'm fairly sure, just based on like model. Anyways.
Yeah. So we basically ask it to look at the data and come up with the best model it can. And in Bayesian terms, and in fact we don't even give it a hypothesis, so to speak. We get it to generate the hypothesis during the EDA phase. So I think it would be. I think we. Okay, I don't know the details of that, but we get it. The EDA thing gets it to generate the hypotheses, and then after that, it's trying to sort of confirm them. A bit like the hypothesis that we saw, where it thought that it would need to model the origin in the model, but then it figured that was not necessary based on the investigation it did. So I hope that answers your question.
Okay, thanks.
Right. Any other question while we finish the setup?
Oh, yeah.
Have you thought about, or maybe you've already done experiments on this, but on data sets that really it won't have seen Bayesian models of before? like to what extent is it like, oh, I know this model?
That is a great question. I mean, we've evaluated this on fairly simple models, and undoubtedly we could give it a situation that it would be beyond what it could do. We don't have a good evaluation for that yet, but that's an interesting thing to think about. I should say what we're doing. This is, I mean, we're publishing, we're presenting this at LAFI', but we hope to write this up as a proper refereed publication. And so that's, that is a kind of question. How do we kind of measure or evaluate what is the space of models, that or data sets that this is actually good for? And I don't know. We can give examples. I'm not sure how we can empirically, establish that kind of question. And one of the difficulties there is that, of course, these models, if we're working with public models, they may well be part of the training set, and so we have that tainting problem.
Maybe another question for this
Sure.
audience.
Sure.
While they're setting that up, from the perspective of people working on this kind of system, what do you see as the value of having probabilistic programming languages for it to hypothesize these models in, versus, for example, having to write all the inference and modeling code itself? And are there like dream languages that we could have for modeling, or is it already, just use Stan? Like, are there does Claude want a better probabilistic programming language to work with?
Yeah, that is a great question. I mean, obviously my bias is that these things are, probabilistic programming languages, allow you to kind of more compactly express the inference code. So I think that helps humans write inference code, and so that you would think that would also help Claude. But yeah, we could experiment. Once we got the system, it's all automatic. So we could, at the moment, it generates Stan, but it's dead easy to get it to say, generate I don't know. Pyro or Church or some other language, or maybe even just build the inference itself and do just do the MCMC from scratch. We could experiment with those kind of things. Yeah, when natural language is a programming language, the details of the kind of conventional programming language sort of starts to matter less and less.
Okay. Let's thank Sandy once again. Thank you very much.
Thank you.